Okay, our last section, simplifying radical expressions. We're going to do all kinds of radicals that we've had in the past, as well as add in now all the cube roots, the fourth roots, fifth roots, and the variety of others, and simplify as we go. So that'll be a big thing. Adding, subtracting, multiplying, all are possible. And then you can see we're going to rationalize the denominator. So let's get started. There are a couple of properties that you definitely need to have seen and worked with, and that is if you have a radical whose root and powers match, then the answer will always be the absolute value of a if n is a positive even integer. So in other words, if it's even, we want, fourth. The fourth root of a to the fourth. If that comes out, it would come out as a, but we want to make sure that's a positive value, so we need to put it in the absolute value signs, okay, to make sure we're getting positive answers. Whereas in the next one, if we say it's an odd, it's always going to come out to be its value, what it is. And so when we look at these, you're going to have to be careful. Are we an odd or an even integer? Okay, so it's the even integers that gets the absolute values to help us remember, and it's the odd powers that are just normal, the variable, that root. Then we have the multiplication of a root, and that is to help you break things down. You can always subdivide that root into other possibilities, and so you can take factors of that number. So if there's a number underneath a root, you can break it up into two smaller factors, so an a value and a b value, anything that multiplies that would be helpful for you to simplify. And then the last one is just the opposite of that. If you can do that with multiplication, why not with division? So if we have a division problem here, you could simplify it and consider the numerator just under that root and the denominator under that root. It would still work just as well. So I'll show you that with some numbers as we go through our simplifying processes. So keeping those properties in mind, we want to start out simplifying. And this first one is a square root. So your brain has to be thinking groups of two. Anything that is a group of two, if I'm a variable, should come out. And the numbers are just like we've always done. So in breaking this down, some people like to say, and this is just a thinking step if you don't want to do too much writing, square root of 81 we know is a perfect square. So I'm just going to squiggle that. Then the x cubed is not a perfect square, but we need to think of it as it's an x squared times an x. That's where you use that one property of breaking it down. So you have one group that's a perfect square and one that's not. And then y to the fourth is a perfect. I'm not going to split it up, but it's basically y to the second times y to the second. And then z to the sixth is also a perfect set of two. So it's even. Think of it that way when you're going for square roots. And so it would come out as half of 6. All right, so perfect combinations of two. As long as you're a combination of two things, you are a perfect square. If you're not, then you're going to stay underneath and be part of the square root. So here we go. Again, squiggling what I thought were my perfect squares. And when we do this, we always like to continue the process of putting our numbers first. So 9 is the square root of 81, and then alphabetical order is what we like, but if all the variables don't end up in absolute value signs, you know, we got that problem. So let's see. If we take a number here and take it to the fourth power, it's definitely going to be positive. So when we take its square root, it's going to come out as a positive number. But I believe these other ones, we really can't tell. An x squared, and I take the square root of it, it's going to come out as x. I want to guarantee that that's a positive number, so it's going to be an x. A z to the sixth will come out as z to the third, but if that was a negative to begin with, I'm going to have to guarantee that z to the third would be a positive. So I'm putting those two in absolute values, so guaranteeing they come out to be positive values. And then we have that one guy who didn't break into anything. He wasn't a perfect combination of 2. And so we leave this as 9y squared times the absolute value of x times z to the third times the square root of x. We can check. I think we're going to be close. Yep. Okay, we got that one right on. And yeah, there's going to be, I don't know what the direction's going to be, because I know later on the next slide I'm going to say assume that all variables are positive. So this is when you don't know what the variables are to begin with, that you have to take this into consideration and use those absolute values. All right, so let's go to a cube root, something different than a square root. We're thinking groups of 3 now is the only way we can come out of this cube root. So you're going to test and see if 125 is a perfect cube root, and I believe you should know that it is. Is x to the 6th a perfect combination of 3 things, or groups of 3, as we'd like to say? Y is not. Y to the 1st, there's only one of those. Z to the 5th is not a perfect combination. You might want to think of that as z to the 3rd times z to the 2nd. So we have one combination in that z that is a perfect, and we have a leftover. So here we go. We should be able to simplify from here. And it's an odd power, so everything should come out as is. We don't have to worry. Or, sorry, it's an odd root. So 125. The cube root of 125 is 5. Then we got our x to the 6th, which is really 2 groups of 3. Then we have our y, which is definitely not a group of 3. Do not forget to put your little cube root there. Then we're looking at the z to the 5th, which we said one of those would come out as a perfect group, and then the z squared would be left underneath. So look at what we have. All combinations, 5x squared z times the cube root of y times z squared. And our answer again looks like it checks. Okay? So simplifying single radicals. Now, here's where I said, now in the very next set of directions, you could maybe see, assume the value of each variable is positive. If that's true, then you're not going to need to worry about the absolute value of different radicals and absolute value sign. So just simplify. Now, there's a slight problem on each of these. When I start in the first one, I'm looking at, wait a minute, that's to the 1/2 power. Well, if you remember, we had 1/2 power is just another way to say I am a square root. So we are really multiplying 2 square roots here. Oops. And if we do that and want to rewrite it so that we're looking at the same thing, there's nothing wrong with that. 64ab to the 5th times radical 8ab to the 6th. Now, if it just says simplify and we're looking to go bigger and better, we can. Sometimes you can simplify what's there, break it down, and then try to multiply. So you've got both choices. Put it together to make it bigger or work with each separate. But we're doing square roots here, so you know, I really don't know what was best. Maybe we could multiply it together, but leave everything sort of separate so we don't have to remultiply. So let's leave the 64 because we know that's a perfect square number. Maybe think of the 8 as 4 times 2. So again, I like my little squiggles. I'm a perfect square, I'm a perfect square, the 2 is not. And then we can multiply the a's. A times a is a squared. Now I'm a perfect square. B to the 5th times b to the 6th is b to the 11th. By itself, it is not a perfect square, but if we break it into the biggest group of 2 that it has, we could say b to the 10th times b to the 1st. So think of it that way now, the biggest even power and then what's left over. So I think we're ready to simplify. Here we go. The square root of 64 is 8. The square root of 4 is 2. Square root of 2 is going to have to stay. The a squared will come out as an a. The b to the 10th will come out as b to the 5th. and I think that b will have to stay. So the only cleaning up I would do here is 8 times 2 is 16, a b to the 5th times the square root of 2b. Again, check your work. So you could have separated them, as was in the problem, rewrote them, and or combine them like we did, but not really totally multiplying it all the way out, because then you got to work backwards if you recognize there's already perfect squares. Our next one, we have the same issue. It's written in power form in the denominator, just like over there, so we need to rewrite this so we're looking at the same thing. If you want to change everything to power form, that's fine. This section's more about radicals, so I'm going to stick with writing radicals. So 9 times the cube root of 48x to the 8th all over, it would be the cube root of 2x to the 3rd. Now in this case, I do believe it makes sense to go backwards on that property, which says we can write this as one big radical, because they are the same style of radicals. They're both cube roots. So we're going to do this. We've got a cube root going on, but we got some fractions. And then we can do the arithmetic with the fractions, and at least this is in your, the head work you want to do before we simplify. All right, 48 divided by 2 we know is 24. Normal division with numbers. X to the 8th divided by x to the 3rd with variables leaves us an x to the 5th. So we've still got a cube root of 24x to the 5th with our 9 out in front. Now ask yourself, are there any perfect cube root numbers in 24? And you should be telling me 8. And there is one set of 3 in that 5 also. So we got some simplifying we can do, and if we go this way this time, that 8 would come out as a 2, but we already have a 9 out front, so that would make it an 18. The 3 would stay underneath, the x cubed would come out as an x, and the x squared would stay also. So now we're going to have a cube root of 3x squared underneath. 18x times the cube root of 3x squared. There we go. It matches. Now that we've done some multiplying, let's do some adding and subtracting. And the rule, if you'll notice, these will look a lot like what we did with our imaginary and complex numbers. Real with real, radical with radical, then you will simplify whatever you can. So we're adding first. So the real part with the real part, because we're adding, 3 plus 8 would give us 11. Gal. Then we have a minus square root of 24 and a plus a negative square root of 96. Now these are square roots. They are not simplified, so it makes sense to go ahead and simplify as we go. What is the biggest perfect square number in 24? I think it's our 4. So we could simplify this to 11 minus, and if this is 4 times 6, that's our biggest perfect square in there, it would come out as 2 root 6 plus, 16 times, no, that's 48. 2 times 48. 16 is a good number there. So 2 times 16 times 3. Yeah, so 6 times 16 would have been the best choice. We broke it down slightly different way, but so that would have been 4 root 6, so a negative 4 root 6. Now we have 2 like terms that can be added. So we've got 11 and a negative 2 root 6 plus a negative 4 root 6 is a negative 6 root 6. So best choice. Again, we like the idea that the real part has to be first, but doesn't always have to be that way as long as you carry the sign. So on this one, be careful because we're subtracting on the next one. And when we subtract, you must carry it. So some of you might want to do that from the beginning. So this subtract would be subtract a negative, which would be plus a positive, subtract a. So you might want to do something like that. You don't have to, but here we go. 4 plus 15 is 19. We've got our radical 27 that we can simplify, plus a negative radical 48. And again, you're looking for what is the biggest perfect square number in each of those. So I'm going to go 9 times 3 for 27 is my best look because we're doing square roots. And we learned that the 48 was a good 16 times 3 from that last problem. So here we go. We'll get 19 plus 3 root 3 plus a negative 4 root 3. Adding and subtracting our like terms, we would get 19 plus, you could say a negative 1 root 3, or you could just say a negative root 3. Your choice how you want to work that. Okay? Now, last but not least, as you know, we've been saying rationalizing the denominator. We're going to multiply and divide. So here's 2 that we're going to multiply on. When you multiply, it looks a lot like FOIL. As best we can say. You're going to be foiling. We got binomials. First, outside, inside, last. There's 4 combinations. You can only multiply real with real and radicals with radicals. But you still can multiply the whole combination. So ready? Here we go. Whoa! First times first. We should get 2 times 9 is 18. Outside times outside. That would be 2 times a negative 7 root 3. Remember, whole number times whole number, radical times radical. We would get a negative 14 root 3. Inside times inside would give us 27 root 3. Last times last would give us negative 21 root 9. Root 9 is better known as 3. So that actually on the end here looks like a 63. We still have our 18 up front. We've got some like terms here. So negative 14 plus 27 looks like a negative, plus 13 radical 3. We still got our negative 63 down there. What do we got? 43. So we got a negative 43 plus 13 root 3. How about 45? We're not doing our math right. 45 and 18. 18 and 5 is 3, carry the 1, yeah. Negative 45 plus 13 root 3. Check it. Better. And last but not least, one with a sign in it, different combination, but first times first would be 9 root 2. So that would have been these 2 together. Outside times outside, there's normal numbers, so just like normal, so plus 3. Inside times inside, the only thing we can multiply is the radical 2, so be careful. We got a negative 3 times radical 4. Radical 4 is really 2, so 3 times 2 is 6, and it's still a negative. And then last times last, we got a negative root 2. Combine what you can. Whole numbers first. We got a 3 and a negative 6 for a total of negative 3. Then we have a 9 root 2 and a negative 1 root 2 for a total of 8 root 2. So negative 3 plus 8 root 2 is what we're looking for, and that's exactly what they got as well. All right, last then would be that division. If you cannot keep a radical in the denominator, you're going to have to get rid of it. And I've got it written 2 different ways here. So if I want to get rid of a radical, we know we can multiply it by itself, and it becomes a whole number. So that's one of the quickest rules to use when you're dealing with these square roots in division. So let's go with, on this one, multiply both the top and the bottom, because again, you want to think of it like we did with imaginary numbers. You want to think of it like that fancy form of 1. Okay, when I say fancy form of 1, that fancy form of 1 does not change our work. Okay, a square root of 6 over square root of 6 divides out to be a 1, but it's in a form that we need to use. So if it's in a form we need to use, ready? Let's use it. On top, we would get 2 root 6. Can't multiply those together. On the bottom, we would get radical 36, better known as 6. When we cancel, we would get root 6 over 3. You cannot cancel within a radical. Remember, radical is not a whole number. So when you finish, did you get root 6 divided by 3? We did. Now, the difference on this next one. We don't just have a simple radical like we had here underneath. We had a 3 minus 7. So think of it more like I'm locked in. I'm a binomial. So now, the only thing we said in complex system when we did these was that a conjugate, a complex conjugate, would make this work. It would get rid of all the i's. Well, the same idea holds true here. If you multiply 3 minus a radical 7 by its conjugate, you will not have any radicals remaining in your work. So our conjugate, if you remember, is the exact same thing, different sign. So we're going to be looking at a 3 plus root 7 that we will multiply both the top and the bottom by to get, again, that fancy form of 1 for multiplying. Okay? I do want to get rid of that fancy form of 1, though, so it's not a distraction in our work. And we are really multiplying two binomials. And again, because your focus on the denominator cannot have any radicals in it, I would definitely start there. So here we go. Here's my big denominator, because we got several things. First times first. 3 times 3, give me a 9. Outsides will be 3 times that positive root 7. So 3 root 7. Insides, negative root 7 times 3 would give us negative 3 root 7. Anybody catch that I can't write what I say? Clean this one up a little. I did say outside 3 root 7, and then I proceeded to write 3 root 3. All right. We're now ready for last times last, which would be right here. It's a positive times a negative, so a negative square root of 7 times square root of 7 gives us square root of 49, better known as 7. And if you haven't seen that along the way, when you multiply a radical by itself, you always get that value that's underneath. So if you can shorten up your work and not go to the 49, that's what we're looking for. All right, simplify. 9 is a like term with the negative 7. That looks like we've got a 2, because these two cancel out, and so our denominator right now is looking like a positive 2. Up on top, we need to distribute is all. 4 times 3 is 12, and 4 times root 7 is 4 root 7. If I put that up here as my numerator, 12 plus 4 root 7. We're looking at, oh, pretty nice, with the exception of I'm a whole number, whole number, whole number that's even. Those all can be broken down, so let's take a factor of 2 out of each. We would get 6 plus 2 root 7, and we should be done. Same as they did. Good job. So you now know how to add, subtract, multiply, divide, and simplify in different styles of roots. And that's what we'll be working on in this last section. So bring any questions you have with you to class.